Hello, welcome back to the channel. In this video we'll see number of possible operations on a improper axis. So if we have improper axis in a molecule, exactly how many operations can be performed on that single improper axis, and what are the consequences of that we shall see, right? So before this, I exactly go with improper axis of symmetry. Let me just illustrate the operations and symmetry element for one more time. This has been described in the first video itself, but to make things clear, and even this particular point I had not mentioned earlier anywhere. So considering that also in mind, so I'm taking this. Consider this molecule ammonia. It's pyramidal molecule where three hydrogens have been represented in this way. Now we know that this molecule, it has symmetry element proper axis C3, which can be represented here, right? So this is axis of symmetry, C3 axis of symmetry, which means that with a reference to this, the molecule, it can be rotated by an angle that is 120 degree to get indistinguishable orientation, right? Now again, just I'll make the things clear for one more time. So this reference on which the molecule is being rotated, that is symmetry element. So here it is called as C3 axis, and the operation that we perform, that is rotation, the molecule that gets rotated on this molecule, this operation thing, that can be called as symmetry operation. So now see, on the same axis, this axis itself, what I can do is I can rotate the molecule on by 120 degree. What I get is this orientation. You can just monitor the changes, H1, H2, H3. They have changed their position. So this H1, it will take up this position upon rotating this molecule by 120 degree clockwise rotation. So this is orientation 2. From orientation 2, the molecule, it has turned to orientation 1, the molecule, it has turned to orientation 2, and now these two, they can be called as indistinguishable. Therefore this C31 whatever I have mentioned here, so that can be called as symmetry operation, and this C3, this is the reference for this operation. So therefore C3, it will be called as symmetry axis. Now on this axis, this is not just the single operation that can be performed. Instead of rotating the molecule on this axis by 120 degree, what I can do is clockwise itself, I can rotate the molecule straight away by say 240 degree. So from here, if I rotate the molecule by 240 degree, straight away I go here, right? See, H1 by 120 degree rotation, it had come here. Now by 240 degree rotation, H1, it should take up this position. You can find it here. So from here to here, on the same axis have not changed. Instead of 120 degree rotation, even if I rotate the molecule by 240 degree, I'll get indistinguishable orientation. So therefore this 240 degree rotation, whatever I am doing on this molecule, that is also symmetry operation itself. 120 degree rotation, that was also a symmetry operation. 240 degree rotation, that is also a symmetry operation itself. And both these operations, they are performed on the same axis of symmetry. So point is that on one element we can have multiple operations. So here on one C3 axis, we have shown now two different operations that are possible, 120 degree rotation as well as 240 degree rotation. So that 240 degree rotation, it changes the molecule from orientation 1 to orientation 3, and this whole 240 degree rotation, it can be identified as C32. So C32, essentially it means that, say C31, if it means 120 degree rotation, then it is C32, it should be 240 degree rotation, right? So usually in books, what they do is from here to here, they mention it to be C32, but technically I feel it is not correct, because here to here again it will be C31 itself. So if you are in orientation 2, to take the molecule from orientation 2 to orientation 3, what you are supposed to do is this 120 degree rotation. So therefore this will be again C31 itself. So it is better to call this orientation to this orientation as C32, right? So now therefore I have shown this is C32. Now further what I can do is not just that. On this axis I can rotate the molecule by 120 degree rotation. I get identical orientation, equivalent orientation, not identical, equivalent orientation. And on the same axis, if I rotate the molecule by 240 degree rotation, I get equivalent or indistinguishable orientation. So further what I can do is I can even rotate the molecule on the same axis by 360 degree rotation. So if I rotate the molecule by 360 degree rotation, so if you can follow the molecule, what it does is from this orientation, it just passes all these orientations and it comes back to this orientation itself. because 360-degree rotation, it should get back the original molecule, right? Or from this point, if I want to go to this, I can say that again it is 120-degree rotation. But now what I want to show you is, from this original orientation, the molecule, it has returned back to this orientation itself. So I can say that it has traced this path. So now the point is that on this axis, the molecule, it can be even rotated 360 degrees to get indistinguishable orientation. Okay, now the point is that on same symmetry element C3, let us say C3, I call it as symmetry element, I can perform three different operations. Maybe I have represented it as C31, C32 and C33. So now just single symmetry element, it has led to more number of symmetry operations, and this is possible whenever we have the element as axis of symmetry. So in other cases, whether it is plane, inversion center or identity, in all other cases, one symmetry element, it will just lead to one operation. But in case of axis, no. Of course, proper axis as well as improper axis. How this changes, they affect when the symmetry element is improper axis, that we shall see soon in the next slides. But when we have proper axis of symmetry, so when proper axis of symmetry is present, multiple operations, they are possible on the same symmetry element. Now in that case, the question arises, how many symmetry operations can be performed on a given proper axis? So if you see here, this is C3 axis. On C3 axis, three different operations I have performed. But out of that, this last operation which returns back to the molecule from orientation 1 to orientation 1 itself. So that can be written as C33. This represents 360-degree rotation. This will be nothing but our identity operation itself. CNN, always it will be identity operation itself. So therefore now it is not necessary to consider this operation separately as a operation, as it will be considered in this identity operation itself. So now we are left with the two genuine rotation operations on a C3 axis. So simply, just based on this, I can conclude that on a Cn axis, n-1 symmetry operations are possible. On a Cn axis, actually n number of symmetry operations are possible, but one, it will be removed as identity. Therefore, n-1 symmetry operations are possible. Hope this again clears you about element of symmetry and operations. So whenever we have proper and improper axis, definitely this question arises, because on same symmetry element, multiple operations will be possible. And if it is proper axis, as I have mentioned, on a Cn axis, n-1 symmetry operations, they are possible. Of course, this point I would have mentioned it along with while demonstrating axis of symmetry itself, that there I have not mentioned it, so therefore I have taken it here again. Now with this background, let's go to possible number of operations on improper axis Sn. Of course, this again, in this case we can consider two cases. So when n is even, this number of operations, it will be different, and when n is odd, number of operations, it will be different. First let me consider when n is even. Try to understand these things, and to demonstrate this phenomenon, I have taken S4 axis. N should be even, so S4 axis has been taken. So now S4 axis, if I have, first I can think of S41 operation, S41. So S41, it can be simplified as, mathematically it can be written as C41 into sigma 1, because that is the definition of S4, proper axis rotation followed by perpendicular reflection. So therefore S41, it can be written as C41 into sigma 1. This cannot be further simplified, so let me keep it as it is, C41 into sigma 1. So I have kept it as it is. Now come to this S42. See, again on the same logic, or even this has been mentioned in my previous video. Of course, to understand certain things here, you need to watch the previous video, where if a operation, if it is performed for n number of times, what will be the result, and that aspect has been discussed, and those results definitely they are considered here to simplify the things. So therefore you should know those facts. Okay, let us come back to this. So S42, it can be written as C42 into sigma square, right? See, now this C42, it refers to on C4 axis 2 times rotation. C4 axis rotation, it means it is 90-degree rotation, and on such 90-degree rotation axis, if we do the operation for 2 times, easily I can say that it is 180-degree rotation. So therefore this C42 even, it can be written as C21. Not necessary, but even it can be written in this way, or even if we keep this in C4.1, C4.2 format itself, nothing wrong. Even this can be performed in even the C4.2, it can be simplified in this way. Okay, I have simplified it, let it be, right? And then further, this is sigma square. Sigma square means it will be E, because the reflection operation, if it is performed for even number of times, it results in E. This result we have seen in previous video. Now, anything, if it is multiplied with identity, so that leaves that unchanged. This we can understand, hope I can understand. So this simply means that one C2 rotation, then again 360-degree rotation. 360-degree rotation does do nothing. Therefore, this leaves, or this S42, it simply changes to C21. C21. Fine. Okay, now similarly, I consider this S43 operation. S43, it can be considered to be C43 into sigma 3. So now here, this C43, it cannot be further simplified. C43, it should be left as C43 itself. It cannot be written in any other way. Whereas this sigma 3, if I need, I can just write it as sigma. Let me do that. So this will be is equal to just C43 as it is have written. And sigma cube, it just represents sigma itself. It's because sigma operation, if it is repeated for say odd times, then it leaves sigma itself. So therefore, now simplification of this S43 can be said as C43 into sigma. So let this be aside. Let this be here. Now we shall go with S44. So S44, it can be written as C44 into sigma 4. We know this fact that C44, CNN, that will be E. Similarly, sigma 4 times. Sigma, if it is repeated for even number of times, it results in E. Again, E into E. That should be E itself. Fine, let me continue. Let me not stop at this stage. Let me just continue. Let me continue S45. What I am doing is, I have completed one 360-degree rotation with appropriate number of reflections. Just after completing 360-degree rotation, again I am going to rotate the molecule on the same axis. Right? Now, next operation, say I perform it to be S45. So in simple way, S45, it can be written as C45 into sigma 1, right? Or even what I can say is that, so here it should be sigma 5 times. Technically speaking, it should be sigma 5 times. Let me do that, sigma 5 times. Now when I simplify the things, C45, it can be written as C41, because C44 is E. So now the C45 means I have rotated the molecule 360-degree and then plus one extra rotation. So when I rotate the molecule by 360-degree rotation, I'll get back the original orientation. From that, one more rotation operation I have performed. So therefore, C45, it will be nothing but C41. Sigma 5 odd number of times, it will be sigma 1. So what I'm left with is C41 and sigma 1, right? And now next, similarly S46, if I consider, so S46 in the same way as I have done it for S42, see, this can be first written as C46 into sigma. Of course, here it is better to write it as sigma 6 itself, so there will be uniformity. This will be sigma 6, fine. Now, so again C46, it can be written as C42. It is because C44 plus 2 more rotations, so therefore this will be C42 itself, and sigma raised to 6 times, it will be E. So therefore this will be C21 itself. See, what you can notice here is that after this S44, you are just repeating the things. S45, that will be nothing but your S4n itself, because S45, it is C41 into sigma 1. S41 is also same thing. S46 is ultimately C21. S42 was also ultimately C21 itself. So even if you continue the things, you will not get any new results or new operations will be possible. Just things will get repeated, right? So what I request you is just repeat this for say S6 you try, S8 you try. So in all those cases you get the nice idea, and you get the things fixed in your mind, and you can convince yourself by working more number of such things. So I sincerely request you to try with say S6 you try, S8 you try. So yeah, by trying all those things, then the results, ultimate results, they will be more convincing than just concluding with this one example here. But let me conclude it with what exactly will be the possible number of operations on Sn when n is even. Let me conclude or let me give you the conclusion with just one example. See, the conclusion, it can be said in this way: when n is even, that is this case, a total number of n number of operations are possible. That's what we have seen here. See, it's n is equal to 4 here, it's S4 axis. So ultimately what we have performed is 4 different operations it was possible. Fifth operation, even if we do, that had resulted in the first operation itself. So therefore from here onwards, if we continue, it will just repeat the things and they cannot be considered to be new symmetry operations. So n number of operations are possible. When n is even, a total number of n operations are possible on that particular improper axis. But you see now, out of these 4, this resulted in E. Identity, it has already been considered. So therefore this S44, I cannot call it as a new operation, because for any molecule, identity it will be considered as separate operation. So S44, that will be is equal to E. So therefore this is not a genuine improper rotation operation. So this will be considered by some other operation. Similarly, if you look at here, S42, it was simplified as 321, or even it can be just left, you can leave this as C42 itself, nothing wrong. C42 or C21, both are identical. Right? Now, this is also considered on rotation axis itself. So rotation operations, pure rotation operations which are possible on that molecule. So in that axis, this operation it will also be considered. Now what we are left with is only these two. Right? So this is genuine improper operation. See, because this cannot be further simplified. So to show this operation, we should perform rotation followed by reflection. Similarly, to show this operation, it is rotation by an angle, then we should perform sigma operation. So therefore these two, S41 as well as S43, these two, they can be considered to be genuine improper operations. So when you work more number of examples, these results, it will be more convincing to you. So that's why I am repeatedly urging you to try S6 and S8 and all. Okay, now with this itself, if at all I have to conclude, what I can say is that, but out of this n number of operations, only n by 2 will be genuine Sn operations. That's what we see here. S4 axis it is, but only 2 are genuine improper operations. So therefore, ultimate conclusion, it is this: when n is even, of course, we can perform n number of operations on that axis, total number of operations possible. But out of that, how many will be genuine improper? That will be just n by 2. So remaining n by 2, they will be identity, and usually they will be covered in other symmetry elements, or usually identity plus proper axis, it will cover remaining all this n by 2. So that is the case when n is even. Now the interesting thing is when n is odd. So when n is what will happen, that we shall see. Same thing we shall repeat. Now for n is odd, the example that I am considering is S3 axis. Let's say S3 axis has been considered on a molecule. So just like in the case of, say, eclipsed ethane that had this axis, if you remember. Fine. Now S31, by definition, it can be written in this way: C31 into sigma 1. This cannot be further simplified, so I leave it as it is. Next, S32, you look at S32, it can be written as C32 into sigma 2. Right? So S32 means 2 times rotation, 2 times reflection. So therefore S32, it can be written as C32 into sigma 2. C32, it cannot be further simplified. C32, I leave it as C32 itself. Sigma square, even number of times if we repeat sigma, that results in E. So therefore C32 into E, this turns out to be, and C32 into E is C32 itself. So S32, essentially it will turn up to be C32. Consider this now. S33, if I do, it can be written as C33 into sigma 3. C33, we know that it is E, because C and N, it will be E. Sigma 3 times, if I repeat, it will be sigma itself, sigma raised to 1, or sigma 3 times if it is repeated, it will be just sigma itself. So E into sigma, it can be written as sigma itself. So S33, it resulted in sigma. Point to be noted here is that if we complete rotation by 360 degree when n is odd, then at that time this rotation, it brings back the molecule to original orientation. But because of the sigma operations, sigma we will be performing 3 times or odd times, because of which the molecule, it will not return back to its original orientation 1, it will not be returned back. So what we get is, after completing this S33 operation, so we get reflection operation performed. The molecule, it will be left in reflection operation performed orientation. So therefore S33 it will be resulted in sigma. Now let me continue. Let me not stop here. So let me just continue. S34 if I perform, S34 it can be written as C34 into sigma 4 times. Again this, now you should be able to make out that C33 it results in identical orientation, and from that one more time rotation, just so therefore it can be C34, it can be written even as C31, and sigma 4 times, as I have mentioned earlier, it will be E. So therefore now S34 it turns out to be C31 into E, which will be nothing but C31 itself. Similarly S35, if I continue with C35 into sigma 5, C35 it can be written as C32, and now sigma 5 is sigma itself. So this we cannot further simplify, so it will be just C32 into sigma as it is. I should leave this. Now S36 if I consider, S36 it can be written as C36 into sigma 6. C36 that should be again equal to E, because C36 that will be nothing but C33 itself. Of course, if you refer to books, so many such results will be available, but definitely it is not possible to remember all such results. So in general, if at all I have to mention this, I can say it this way, say Cn axis, and here raised to 2n, 3n, 4n, where n is integer, all those it results in E. So that kind of results, so many general results, we can see them in books, but I'm not considering it because it's very difficult to remember, and wherever it is necessary, we should be able to, if we have developed clear picture, we will be able to say what the outcome will be. So now C36 that should be simply equal to E, because C36 that simply shows that the molecule, it has been rotated on T3 axis for 720 degrees, 2 times 360 degree rotation, so which will essentially result the molecule in leave the molecule in first orientation itself, so it can be called as E. Sigma 6 it will be E, so now S36 that will be E. Fine, now I'll continue. I'll not stop at this stage too. I'll just continue. S37 if I perform, S37 it can be written as C37 into sigma 7, and C37 it can be written as C31. It's because C36 plus C31. So C36 it will be nothing but E. So therefore C36 into C31 that will ultimately result in C31 itself. So therefore this C37 it will be C31, sigma 7 it will be sigma. So C31 into sigma. As you can see, it started repeating the things. Here also you have C3 into sigma. So S37 it's as good as S31. S38 in similar way, it just results in C32, which is nothing but our S32. So which simply means that when n is odd, we can have total 2n number of operations. 2n number of different operations are possible. After that operations, they just start repeating. Right now, ultimately conclusion what can be drawn, that we shall see. Again same thing, I urge you to work, say S5 you can try, S7 you can try, S9 you can try, all those things you can try, and compiling all those results, based on that you can convince yourself, or you can understand very conveniently that whatever result I have given, it is definitely a valid result. So now just based on this example, I am giving this result. When n is odd, a total of 2n number of operations are possible. You have seen that here, because in this case, just if I stop at this stage, it is not returning back the molecule to E. So that is the indication that further operations are possible. So I went up to this S36, and every time I got different operations. So therefore on a S3 axis, or when n is odd, total number of 2n operations they are possible. 2n different operations are possible on same improper axis. Out of that, which are genuine improper and which turns out to be some other operations, that fact if you check, see, this is genuine improper operation, C3 into sigma, whereas this turned to be simple rotation, this turned to be simple reflection, this turned to be simple rotation, and this one S35 it is genuine improper axis, and this one it turned out to be identity. So therefore just out of this, though totally 6 operations have performed, so out of that only what I can find is 2 operations, they are genuine improper operations. So if you perform this for S5 and S7, on that fact again you can conclude, or you can come to this conclusion in a very easy way, right? But out of which, out of these 2n operations, only n minus 1 will be genuine Sn operations. So S3 it is, so therefore 2 operations, n minus 1 is 2 here, so 2 operations they will be genuine improper axis operations, others they turn out to be other simple operations. So that is the conclusion that can be drawn when n is odd, right? So my sincere request is to try this exercise for other axis. Maybe what I should say is you should start from simple S2 and then you should go up to S10. For all these things you should write. So only by practicing and only by imagining things, of course here it is just mathematical, nothing to imagine, but when it comes to symmetry, more number of examples you need to work out, and you should imagine the things, symmetry elements, symmetry operations, all those things you should imagine it in your mind. So then only you can develop grip over this subject. Otherwise definitely it turns out to be very difficult. It's because it involves a lot of imagination. So to begin with, you can of course take the help of symmetry at Otterbein 3D animations. You can take help of, or if you can develop models, that's good. If you don't have models, at least work or play with the molecules in that symmetry at Otterbein gallery. So many molecules you have, so that you will be convincing yourself about symmetry elements and symmetry operations. Okay, hope this video has helped you and it has cleared the facts which I have mentioned. And if you have liked this video, you can just give a like and you can share this video to your friends. Subscribe to this channel if you have not subscribed, and you can press the bell icon to get the quick notifications of next video. Thank you for watching this video. Thank you again.